Welcome back. We are going to talk now about the div instruction. The div instruction divides one number by another number. Again, strictly speaking, unsigned division, which means we don't consider numbers with sign, like we don't consider negative and positive numbers at this point. We only consider positive numbers. It looks like this: div and arg, which is the only argument of this instruction. It is actually the opposite of mul, because mul multiplies numbers, and also all those strange registers that are used for the result are going to be used in div, but in the other way. We are going to see it in a moment. It has some forms, just like the mul instruction has some forms. The very first form, or maybe the oldest one, historically speaking, is the case of arg of size 8 bits. Arg is the number used for division. That means that this is the action which is going to be invoked. At the same time, two things are going to happen. Ax is going to be divided by arg. This is the usual division that you know, but it has an integral result. It doesn't have a floating point result. It's not a fraction. The result is going to be a whole number, an integer. This is called the quotient, the result of the division. Ax is divided by arg, and the result is going to be stored inside al. At the same time, the instruction is going to find out the remainder of ax divided by arg. This is how we represent remainder, by the percent symbol. Okay, some people call this the modulo, which is the same. This is just the remainder when dividing ax by arg. And the result is stored inside ah. This is called the remainder. The div instruction is pretty interesting. Two things happen at the same time: the division, which gives the quotient, and the modulo, which gives the remainder. The quotient is stored inside al, and the remainder is stored inside ah. The next form is, of course, as you probably expected, argument of size 16 bits. This time, we are going to divide the number represented by dxax by arg. We actually do dxax divide to arg, and we get a result that is stored inside ax. This is actually reasonable, because dxax is a large number. It is of size, this one is 16 bits and this one is of 16 bits. Together it is 32 bits. 32 bits divided to 16 bits, we mostly expect to get a result of 16 bits. This is not always correct, but if we think about it, dividing something large by something half the size of the bits, is supposed to give something half the size of the bits. And just like the first form, at the same time, dxax is divided to arg, and the remainder is found out. The remainder is stored in dx. At the same time, the result of the division is stored inside ax, and the remainder is stored inside dx. The third form is, of course, of size 32 bits. This time, we are going to divide this number, eax, by arg. The quotient is going to be stored inside eax, and as usual, the remainder is going to be stored inside edx. Some examples for using the div instruction. Div ch. This instruction divides ax by ch and stores the division result inside al. The remainder is stored inside ah. I remind you that ch is of size 8 bits. The next one, div esi. Esi is of size 32 bits. So this instruction divides edx, eax by esi. it stores the quotient inside EAX. It also stores the remainder inside EDX. Next example, div DI. This instruction divides DXAX by DI. It stores the quotient inside AX. It stores at the same time the remainder inside DX. As usual, we are going to consider some invalid example. This time it will be div 5CAH. What's the problem here? You might be thinking this is probably going to divide maybe EDXAX by this number. Well, it is reasonable, but the reality is that there is no such opcode. If you want to divide by this number, first make sure to put it inside some register, and only then invoke the div instruction together with this register as an argument. You can't do this directly. As I said, there is no very logical reason for this. This is just the way it is in the x86 architecture. At least these days. Maybe in the future it would be possible. I don't know. Exceptions. At this point, you might have wondered what happens if, for example, you divide a number by 0. Maybe you used to program in some other programming language and you know that dividing by 0 gives some kind of error. Or maybe you just remember from school that you can't actually divide by 0, you don't get a real result. So something strange is supposed to happen when you try to divide by 0. And you can actually do it with the div instruction. If you put 0 inside some register and then invoke the div instruction with that register as an argument, you are going to divide by 0. The processor actually has some kind of way around it, and we are going to talk about it only a little, because there is some complexity behind it. Maybe in the future we are going to talk about it a bit more. The thing we are talking about is exceptions. The processor raises exceptions whenever something wrong happens while running your code. The operation system and the processor work together to handle those exceptions. Those exceptions that we are speaking about here are maybe something very abstract for you. There are some kind of mechanism inside the processor which helps the processor, and maybe in this case we're speaking about the Windows operation system. The Windows operation system together with the processor manage to work together to handle those instructions. The operation system uses those mechanisms inside the processor to handle situations like division by 0. We are going to see some other kind of exceptions or bad things that you can do with the processor. Usually, if there were no exceptions, it would just die. For example, if you try to divide by 0, or maybe even if you try to write something into memory that you don't own, or read from memory that you don't own. And there are so many other examples. Whenever you do something like this, the operation system is informed about some program that try to do something strange. Then the operation system has to decide what to do with it. Sometimes you can ask the operation system to give you back the error so you can handle it yourself with your own code. We might be able to do this in the future in one of the lessons. Let's speak about some specific exceptions that could be raised by the div instruction. The first one is division by 0, which we just spoke about. If we try to divide by 0, an exception is raised. Another example, quotient overflow. This is less trivial than division by 0, but it's not very complicated. If we try to divide a very large number by a very small number, then the quotient will be too large and it won't have space in the location allocated for it. Let's look back, for example. For example here, let's look at this example. If we try to divide by ch some very large number, for example, if ax is going to contain some very large number and ch is very small, maybe if ax is all f's, like ff, ff, and ch is just 1, then this division is going to try to put the result inside al, and there is not enough space inside al to put the result. So an exception is going to be raised.